So, here's something worth thinking about as you settle in tonight. Most of the atoms in the water in your body are hydrogen, and every one of those hydrogen nuclei is about 13.8 billion years old. They were made in the first few minutes of the universe. Nothing has happened to them since. They have been through stars and oceans and other bodies, and they are lying in this bed with you now, unchanged since the beginning. So the story I want to tell you tonight is in some real sense your own. All of it, in order, from the first sliver of a second to the last flicker of light in the far future. It is a long story, and we have hours. You don't need to follow every step. You don't need to hold anything in your head. If you drift off somewhere along the way, that is perfectly fine. The ideas will still be here in the morning, and so will the universe. So let's start where the story actually starts. Or rather, as close to the start as anyone can honestly get. 13.8 billion years ago, everything that is now the observable universe was packed into a space smaller than an atom, hotter and denser than anything that has existed since. That is the picture. And it is worth being clear about what that picture is and is not, because this first part of the night is where most of the confusion lives. The universe did not begin as a small object sitting in empty space. There was no outside to sit in. There was no room around it, no vantage point from which to watch it, no clock ticking somewhere else. Space itself was in there. Time was in there. When people say everything was concentrated in a tiny volume, they mean that every part of space that you can now see, the whole 46 billion light-year sphere of it, all the galaxies and all the dark matter and all the light, was crowded together with no space left over. Not a dot in a void, just a dot. And it was not an explosion. This is the single most misleading word in all of cosmology, and it has been stuck to this subject for 75 years now, mostly by accident. An explosion has a center. It throws material outward into surrounding air. Nothing about the early universe did that. What happened was expansion, which is the same everywhere at once, with no favored spot and nothing to expand into. Every region simply became less crowded, and distances grew. There was no bang, no boom, no shockwave rolling outward, and no place you could have stood to watch it happen. The name came from a radio broadcast. In 1949, the British astronomer Fred Hoyle was talking on the BBC about rival ideas for the origin of the universe, and he described one of them as a Big Bang. He preferred a different picture himself, one in which the universe had always existed and new matter quietly appeared to fill the gaps. He lost that argument, but his phrase, which was casual and possibly a little dismissive, outlived his theory and became the name of the thing he did not believe in. And it is a terrible name that appears to be sticking. Now, the first thing to say about the actual beginning is that nobody knows what happened at it. That is not a failure of effort. It is a genuine boundary. If you take the equations of general relativity, Einstein's description of gravity and space and time, and run the expanding universe backwards, the equations do something ugly. Density goes to infinity, temperature goes to infinity, and curvature goes to infinity. The mathematics stops producing numbers and starts producing the word infinity over and over, which in physics is almost always a sign that you have pushed a theory past the point where it applies. It is not a description of a real place. It is a signpost saying the map ends here. So there is a moment, right at the front of the story, that the story cannot reach. And it has a name. The Planck time. It is the shortest interval that has any clear physical meaning, and it is small in a way that is difficult to hold in the mind. Writing it out as a decimal takes 43 zeros after the point before you reach the first digit. Compared to 1 second, 1 Planck time is roughly what 1 second is compared to a span of time vastly longer than the age of the universe. It is the smallest tick anyone can define. And within that first tick, all 4 of the forces we know about were probably one thing: gravity, electromagnetism, and the 2 nuclear forces, undivided. To describe that properly, you would need a theory that combines quantum mechanics with gravity, and no such theory exists in finished form. String theory is one attempt. Loop quantum gravity is another. And neither has been tested, because the energies involved are absurdly beyond any machine that could be built. So we sit at the edge of that and admit it. And what about before? Was there a before at all? There may have been no first moment at all. Some models have the universe as a bounce, a contraction that reversed. Some have it emerging from a background that was always there. Some have inflation running forever in a much larger space, butting off pockets like ours endlessly, in which case our 13.8 billion years is the age of our bubble and not of everything. And some suggest the question of what came before is malformed, because before requires time, and time is part of the thing being asked about. There is something restful in that, I think, rather than frustrating. The oldest question anyone has ever asked is still open. It has been open for as long as there have been people to ask it, and it will probably still be open long after tonight. But we don't need it answered to continue, because the universe becomes describable extraordinarily quickly, not at 0, but very close to it. And the physics of what happens next is understood well enough that we can walk through it slowly, second by second, then year by year, all the way to your bedroom. So let the beginning go. We will pick the story up a hair's breadth after it starts, and from there, the road is clear. Here is where things get strange in a productive way, because the very first thing the universe seems to have done, before it made a single particle of ordinary matter, was to grow at a rate that makes everything since look like it is standing still. The idea is called inflation, and it arrived in 1980 from a young physicist named Alan Guth, who was at Cornell and worrying about something else entirely. Similar ideas had been circling. Alexei Starobinsky in Moscow had written down a closely related model a couple of years earlier, and Andrei Linde and others reshaped it afterwards into the version most physicists use now. But Guth was the one who saw what it would fix, and what it would fix were 2 problems that had been quietly embarrassing cosmology for years. The first is called the horizon problem. When you look at the oldest light in the sky, the glow left over from when the universe was young, it has almost exactly the same temperature in every direction. Not roughly the same to within about 1 part in 100,000. And that should be impossible. 2 patches of sky on opposite sides of you have never been in contact. Light has not had time to cross from one to the other in the whole history of the universe. They could not have swapped heat, or settled into agreement, or influenced each other in any way at all. So why do they match? The second is the flatness problem. Space, as far as anyone can measure, is geometrically flat. Parallel lines stay parallel. The angles of a large triangle add up the way they did in school. That sounds unremarkable until you work out how finely tuned it has to be. Any small departure from flatness in the early universe would have grown enormously over billions of years. For space to be as flat as it looks now, the early universe must have been flat to something like 1 part in a very large number indeed. That is not the kind of coincidence physicists enjoy. Inflation handles both with a single move, Suppose that in the first unimaginably brief instant, some field-filling space had an energy that made the expansion accelerate violently, not gently, doubling in size, then doubling again, then again, dozens of times over, in a span of time so short that writing it as a decimal takes more than 30 zeros after the point. By the end of it, a region far smaller than a proton had been stretched to something larger than a grapefruit. Which sounds modest until you remember what was being stretched. And both problems dissolve. The sky matches in every direction, because every part of it really was in contact once, in a tiny patch that was smoothed out and then blown up. And space looks flat, for the same reason the ground outside looks flat. Take any curved surface and enlarge it enough, and the piece in front of you becomes indistinguishable from a plane. And then inflation did something that matters more than either fix, something that reaches all the way to you. Quantum mechanics does not permit perfect stillness. Even in empty space, fields jitter. Tiny fluctuations appear and vanish constantly, far too small to see, existing on scales below the size of an atomic nucleus. Ordinarily, they cancel out, and nothing comes of them. But inflation caught them mid-jitter and stretched them along with everything else. Fluctuations that were subatomic became fluctuations the size of galaxies, frozen in place, made permanent by the expansion before they had a chance to average away. Those stretched ripples became the slightly denser and slightly emptier regions of the young universe. The denser ones pulled in more material, which made them denser still, which pulled in more. Over billions of years, that patient process built every structure there is. And galaxy clusters sit where the ripples were dense. The great voids sit where they were thin. And the Milky Way is standing in one of those ancient overdensities right now. So the arrangement of matter in the universe, the reason there are galaxies at all, rather than a bland even mist, appears to be a photograph of quantum noise from the first fraction of a second, enlarged beyond all recognition and never developed further. Everything you have ever seen or touched formed inside one of those ripples. Now, inflation is not proven. It is worth saying that plainly. It fits a striking amount of data, particularly the fine pattern of hot and cold spots in the oldest light, which matches what stretched quantum fluctuations should look like with unsettling precision. But what was the inflating field? Why did it switch on? And why did it stop? Nobody knows. There are competing accounts. There are respected physicists who think the whole framework is too flexible to be tested properly. The strongest possible confirmation would be a particular twist in the polarization of the oldest light, a fingerprint of gravitational waves from that first instant. And after 2 decades of increasingly careful searching, nobody has found it yet. So hold inflation loosely. It is the best account we have of why the universe is smooth and flat and lumpy in exactly the right way, and it may still turn out to be wrong. What is not in doubt is that the expansion happened and then calmed to a walk. Inflation ended. The energy that had been driving it poured into a bath of particles, filling space with heat. This is sometimes called reheating, which is a slightly odd name for the event that put the matter into the universe in the first place. And at that point, the clock is still barely running. We are a tiny fraction of 1 second into the story. Nothing familiar exists. No atoms, no light as you would recognize it, no structure, just an unimaginably hot soup expanding, beginning to cool. But it is a soup with rules now. And from here on, we can follow them. So let's follow them. We are inside the first second now, and we are going to spend a while here, because more happens in this 1 second than in the next 9 billion years. The soup is a plasma of everything. Quarks, which are the building blocks of protons and neutrons, electrons and their heavier cousins, neutrinos, which barely interact with anything, photons of light, and the antimatter versions of all of them in almost equal numbers, and nothing is bound to anything else. It is too hot for that. Any structure that tries to form is immediately smashed apart by the next collision. The temperature is somewhere in the region of 1,000 trillion degrees and falling. And at first, even the forces are not fully separate. Electromagnetism and the weak nuclear force, which today behave completely differently, were once a single, unified force. That unification is not speculation. It is the part of this story that has been checked in a laboratory. The theory that predicted it won a Nobel Prize, and the particles it required were found at CERN in 1983, sitting exactly where the equations said they would be. So what separated them? The Higgs field. Now, the Higgs field gets described badly almost everywhere, so let me try to be careful. It is not a thing floating in space. It is a property of space, present everywhere, including in this room, including inside you. What matters for tonight is that it has a switch. Above a certain temperature, its value sits at 0, and it does nothing. Below that temperature, it settles into a non-zero value and stays there. And the universe crossed that temperature at roughly 100 picoseconds, 1/10,000,000th of a second in. When the field settled, particles that had been massless suddenly had mass, not because they absorbed anything, but because their interaction with the field now cost them something, and it made them harder to accelerate, which is what mass is. And electrons became electrons as you know them. The weak force became feeble and short-ranged, which is why radioactive decay is slow. And that is why the sun burns for billions of years instead of going off all at once. That single transition, 10 billionths of a second in, is why chemistry is possible. Without it, there are no atoms, no molecules, no stars, no you. And it happened before the universe was a full second old, and it is never reversed. The Higgs boson itself, the ripple in that field, was finally detected at the Large Hadron Collider in 2012, 48 years after Peter Higgs and several others independently predicted it, and he was 83 when the call came, which is a long time to wait for a phone call about something you worked out in your 30s. And now we come to what I think is the strangest event in the whole first second. The reason there is anything here at all. In that early plasma, matter and antimatter existed in almost equal amounts. When a particle meets its antiparticle, both vanish, and their energy leaves as light. That is not a rare event or an exotic one. It is what always happens. So as the universe cooled and particles could no longer be freshly created from the ambient heat, everything should have annihilated. Every quark should have found an antiquark. The result would have been a universe of pure radiation, expanding and dimming forever, with no matter in it whatsoever. There would have been no stars and no planets, nothing to look at and nobody to look. And that is not what happened, obviously. And the reason is that the balance was very slightly off. For roughly every billion antiquarks, there were about 1,000,000,001 quarks. And that is the whole margin. 1 part in 1,000,000,000. Everything annihilated, almost. The photons released in that great cancellation are still here, and they outnumber the surviving matter particles by about 1,000,000,000 to 1, which is how we know the ratio in the first place, and it is written into the sky. And the leftovers, that 1 part in 1,000,000,000 that had nothing to pair with, became all of it. Every galaxy, every star, every atom in your hands. You are made of the rounding error. So why was the balance off? Why 1 part in a billion, rather than an exact match and an empty universe? That is genuinely unsolved. It has a name, baryogenesis, and it has conditions, which the Soviet physicist Andrei Sakharov worked out in 1967. He showed that to end up with more matter than antimatter, the universe needed to break certain symmetries and to fall out of equilibrium at the right moment. And the standard model of particle physics does break those symmetries, which was a promising sign. It just does not break them anywhere near enough. The predicted asymmetry comes out far smaller than the one we observe, so something else was going on. Perhaps heavy neutrinos decaying unevenly. Perhaps physics at energies we cannot reach. There are experiments running now, looking at tiny differences in how matter and antimatter particles decay, hunting for the missing piece. Nobody has it. I find that a comfortable thing, rather than an uncomfortable one. The reason anything exists is an open question, and the universe carried on regardless. And here you are, lying in the dark, made of the surplus. By 1/1,000,000th of a second in, the temperature has dropped enough that quarks can finally stick together. They bind in threes, and those triplets are protons and neutrons. Before this moment, there were no protons anywhere in the universe. After it, there are, and they will last essentially forever. At around 1 second, the neutrinos give up on the rest of us. They stop interacting and simply fly free, and they have been flying ever since. And those neutrinos are still around, something like 300 of them per cubic centimeter, everywhere, including in the space your body currently occupies. Trillions of them are passing through you every second, from the first second of the universe, and not one of them will touch you. They are the oldest thing anyone has ever tried to detect. Has anyone managed it? Not directly, not yet. They are simply too gentle. So that is the first second. Forces separating, mass switching on, a near total annihilation that left a residue, and the first protons in existence. Now the pace slows. From here we can start counting in minutes. Between roughly 10 seconds and 20 minutes, the universe cooks. This is the episode that the physicists call nucleosynthesis, and it is where the hydrogen in your body was finalized. The setup is this. Space is full of loose protons and neutrons, still far too hot for electrons to settle around them. But it is cooled enough that if a proton and a neutron collide, they can stick. That combination is deuterium, a heavy form of hydrogen, and deuterium is the doorway to everything else. Add another neutron, and you have tritium. Add a proton to that, and you have helium. Once helium starts forming, it forms fast, because it is a remarkably stable arrangement, and the reactions strongly favor it. There is a clock running against all this, though, and it is the reason the recipe comes out the way it does. A neutron on its own is unstable. Left alone, it decays into a proton in about 15 minutes on average. So the universe was losing neutrons the entire time it was trying to use them. Whatever fusing was going to happen had to happen quickly. And then the window shut, because the expansion pulled everything too far apart and too cool for fusion to continue. When the window closed, about 20 minutes in, the accounting looked like this. Roughly 3/4 of the ordinary matter in the universe by mass was plain hydrogen, a single proton. Roughly 1/4 was helium, and then trace amounts of deuterium and of lithium at the level of a few atoms in every 10 billion. And that was it. Nothing heavier. No carbon, no oxygen, no iron and no gold anywhere in the universe. So why did it stop there? Why no carbon, when carbon is only 3 helium nuclei stuck together? The reason is a curious gap in the periodic table. There is no stable element with 5 nuclear particles, and none with 8 either. So the chain from helium upward has a broken rung in it, and in the brief, warm window available, nothing could get across. Building carbon requires 3 helium nuclei to meet essentially at once, which needs the crowded, patient interior of a star and hundreds of millions of years. So the young universe was hydrogen and helium, and almost nothing else. Every other element you have ever encountered was manufactured later, inside stars, and we will get to that. The prediction of all this came from George Gamow and his student Ralph Alpher, working in the late 1940s. Their paper was published in 1948, and Gamow, who had an incorrigible sense of humor, added the physicist Hans Bethe to the author list purely so that the byline would read Alpher, Bethe, Gamow. Bethe had not worked on it, and he did not seem to mind. Robert Herman, who genuinely did work on it, gets less credit than he should, largely because Gamow could not persuade him to change his name to Delter. But the physics was serious, and it has held up better than almost any prediction in the history of the subject. Calculate the expected hydrogen and helium fractions from first principles, then go and measure the oldest, least contaminated gas clouds and the atmospheres of the oldest stars. The numbers agree to within 1% or 2, and that agreement is one of the strongest reasons anyone believes in a hot early universe at all. You cannot make 1/4 of everything helium by any other means. There is one loose thread, and it is honest to mention it. The predicted amount of lithium is about 3 times more than what is actually observed in the oldest stars. This is called the lithium problem, and it has been sitting there for decades. It might be that the stars destroy their own lithium in some way not fully modeled. It might be something else. It is a small thread on an otherwise excellent piece of tailoring, but nobody has tied it off. So we are 20 minutes in. The universe has its ingredients: hydrogen and helium, a great deal of light, dark matter doing whatever dark matter does, and neutrinos streaming out to the horizon. And then nothing much happens for a very long time. Which brings us to the longest boring stretch in the history of everything: 380,000 years of fog. So what was the universe actually like during all that time? It is worth describing slowly, because it is a genuinely strange condition, and it has no modern equivalent anywhere. There is no place you could go today to see it. Space was filled with a glowing plasma, bare nuclei, mostly hydrogen and helium, and free electrons wandering separately, and light everywhere, and the light could not get anywhere. Free electrons are extremely good at scattering photons. A photon would travel a tiny distance, hit an electron, ricochet in a random direction, travel a tiny distance, hit another one. It was doing this constantly, in every direction, forever. So the universe was bright and completely opaque at the same time, blinding and blank. If you had eyes, and you would not have survived to use them, you would have seen an even glow in every direction with no features in it at all, like being inside the sun. That is not a loose comparison. The interior of the sun is opaque for exactly the same reason, and the surface of the sun is where the plasma finally becomes transparent, which is why the sun looks like it has a surface at all despite being a ball of gas. For 380,000 years, the whole universe was the inside of a star, and during that fog, something was happening that would leave a permanent mark. The plasma and the light were locked together, and that combination behaved like a fluid. Gravity pulled matter into the denser ripples left over from inflation, but the pressure of all that trapped light pushed back out. Pull in, push out, pull in, push out. Sound waves, actual pressure waves, running through the entire universe, on scales of hundreds of thousands of light years. And those waves are real, and they are still measurable. The distance a wave could travel before the fog cleared became a fixed length scale, frozen into the distribution of matter. And galaxies today are very slightly more likely to be found at that separation from each other than at any other. It is a ruler laid down by the first 400,000 years, and modern surveys use it to measure the expansion of the universe. Cosmologists call it baryon acoustic oscillation, which is an accurate name and a joyless one. It is the ringing of the young universe, still faintly audible in the arrangement of galaxies. Then, at 380,000 years, the fog lifted. The temperature had fallen to around 3,000 degrees, which is cool enough for a proton to hold on to an electron without it being immediately knocked loose again. Across the universe, in a span of a few thousand years, nuclei and electrons combined into neutral atoms. The first atoms, hydrogen and helium, complete with their electrons in place. And the moment the free electrons were gone, the light was free. Nothing left to scatter off. Photons that had been bouncing helplessly for hundreds of thousands of years suddenly found the road open and left in straight lines, all at once, in every direction. Physicists call this recombination, which is another poorly chosen word, since nothing was recombining. The electrons and nuclei had never been combined before. It was the first time. And that light is still traveling. It never hit anything again. It has been crossing space for 13.8 billion years, stretching as the space it moves through stretches, cooling as it stretches. It left as a fierce orange glow, roughly the color of a dying ember, and it has now been stretched so far that it arrives as microwaves, cold ones, 2.7 degrees above absolute zero. And it is here, in this room, passing through your walls and through your body constantly, from every direction at once, arriving from the last moment the universe was opaque. It is the oldest light there is, and there is no older light possible, because before this, the universe could not release any. We call it the cosmic microwave background. It is the single most informative object in all of astronomy, and it was found by two people who were not looking for it and who spent months trying to make it go away. In 1964, Arno Penzias and Robert Wilson were working at Bell Labs in Holmdel, New Jersey, with a large horn-shaped antenna built for early satellite communication. They wanted to use it for radio astronomy, which meant they first had to account for every source of noise. And there was noise they could not account for. A faint hiss, the same in every direction, present day and night, unchanged as the earth turned and as the seasons passed. And they checked everything. They ruled out the ground, the atmosphere, the electronics, New York City. They found a pair of pigeons nesting in the antenna and evicted them, and cleaned out what Penzias later politely described as a white dielectric material, and the hiss remained. They were, by all accounts, thoroughly annoyed. Meanwhile, about 30 miles away at Princeton, Robert Dicke and Jim Peebles and David Wilkinson had worked out that if the universe began hot, there should be leftover radiation at a few degrees above absolute zero, and they were building an antenna to look for it. And a phone call connected the two groups. Dicke put the receiver down and told his team they had been scooped. Penzias and Wilson received the Nobel Prize in 1978. Dicke's group, who knew what they were looking for, did not. And Gamow, Alpher, and Herman, who had predicted radiation of roughly this temperature back in the 1940s and been almost entirely ignored, were not included either. Alpher was reportedly bitter about it for the rest of his life, which seems fair. For a while, that old light looked perfectly smooth. Too smooth, in fact, Because a perfectly even universe cannot form galaxies. There had to be structure in it. In 1992, the COBE satellite finally found the variations, and they were tiny. Temperature differences of about 1 part in 100,000. Slightly warmer patches, slightly cooler patches, arranged in a specific pattern across the whole sky. And those patches are the ripples from inflation, photographed at 380,000 years old. Every galaxy that exists grew from the warmer ones. Later missions, WMAP, and then Planck, mapped that pattern with extraordinary precision, and the pattern is where nearly all our numbers come from. The age of the universe, the amount of ordinary matter, which is about 5%, the dark matter, about 27%, dark energy, the remaining 68 or so, the flatness of space, all of it read off from the fine grain of a photograph taken before there were any stars to photograph, 13.787 billion years, give or take 20 million. That is the current figure, and the precision on it is remarkable given the subject matter. There is one small pleasure I want to give you before we move on. Older televisions, the kind with an aerial, would show static when tuned between channels. A very small fraction of that static, roughly 1% of it, was this light. The afterglow of recombination, picked up by a set-top aerial and displayed as flecks on a screen in someone's living room. People used to leave it on by accident. So the fog has lifted, and the universe is transparent, and everything goes dark. This is the part of the timeline that gets skipped, and it lasted a very long time. When the light left, it left. Space became clear and full of neutral hydrogen and helium gas, and there was nothing in it producing any new light at all. No stars had formed. The old glow faded from orange through red into invisible infrared as it stretched, and for something between 100 and 200 million years, the universe was genuinely dark. Not empty. Dark. There was material everywhere, cool gas drifting, gathering slowly, but nothing shining. If you had been there with human eyes, you would have seen nothing whatsoever, for 100 million years, in any direction. Astronomers call this period the Dark Ages, and unlike the historical Dark Ages, the name is entirely accurate, and nobody is arguing about it. And through that darkness, gravity was working. Dark matter did most of it. Whatever dark matter is, and nobody knows, it does not interact with light, and it does not feel pressure. So it had no way to resist collapse, and no reason to bounce back out. It had already begun clumping into halos, while the ordinary matter was still trapped in the fog, unable to gather because the light pressure kept blowing it apart. Once the atoms formed and the light let go, the ordinary gas was free to fall, and it fell into the gravitational wells dark matter had already dug. And that is the sequence. It matters. Dark matter built the scaffolding, invisibly first. Everything visible came afterwards and settled into a shape that had already been decided. Gas pooled at the bottom of those wells. It became denser. As it fell, it heated up, and heat creates pressure, and pressure resists further collapse. So to keep collapsing, the gas had to shed heat, and the only way to shed heat is to radiate it away. This is where the first stars had a real problem, and it is a chemistry problem, not a physics one. Gas cools efficiently when it contains heavy elements. Carbon and oxygen radiate away energy easily, but there were no heavy elements. There was hydrogen and helium and nothing else, and pure hydrogen is a poor coolant. The only thing available was molecular hydrogen, 2 hydrogen atoms bound together, which radiates weakly and is easily broken apart. So the first collapses were inefficient and slow. Why does that matter? because the gas clouds had to grow very large before they could contract at all, and when they finally did collapse, they made enormous objects. The first stars, which are called Population 3, were probably monsters. Tens of solar masses at the low end, and possibly hundreds, blazing hot, blue-white, and completely unlike anything in the sky now. And they lived fast. A star that massive burns through its fuel in perhaps 2 or 3 million years, which is nothing. Then it dies, violently, and nobody has ever seen one. Not directly. They are the most confidently predicted objects in astronomy that remain entirely unobserved. Every one of them died long ago, and they were so far away in space and time that even Webb cannot resolve an individual example. There have been claims of indirect detections, including a radio signal reported in 2018 that would have pinned the first starlight to about 180 million years. But that result has never been independently confirmed, and several groups looking for the same signal have not found it. So it sits as a maybe. What we do know is that when those first stars died, they changed everything. Their cores had fused hydrogen into helium, helium into carbon and oxygen, and on up toward iron. When they exploded, they scattered those elements into the surrounding gas. The first carbon in the universe, the first oxygen, the first nitrogen, silicon, magnesium, iron. Before those stars, the universe contained no oxygen at all. The atom that makes up most of your body weight did not exist anywhere, and then a star died, and it did. And once heavy elements were in the gas, cooling got easier. The next generation of stars could form from smaller clouds, which meant smaller, longer-lived, more ordinary stars. The pattern that still holds today. The universe became fertile after its first funerals, and it has been recycling ever since. So there is light in the universe again, for the first time in 100 million years or more. And the light does something to the gas around it. Those first stars were furiously hot, which means they poured out ultraviolet radiation, and ultraviolet radiation strips electrons off hydrogen atoms. So around each early star and each early cluster of stars, a bubble of ionized gas opened up in the neutral fog. Small at first, then larger, then overlapping with the bubbles of neighbors until the bubbles joined and the neutral hydrogen between them was almost entirely gone. This is called reionization, and it took a long time. It began perhaps 200 million years in and was not finished until the universe was around 1 billion years old. And it is the last global change of state the universe has ever undergone. Since then, the intergalactic gas has stayed ionized and thin and transparent, and it will presumably stay that way forever. How do we know it happened? Quasars. When you look at very distant quasars, which are brilliantly luminous cores of young galaxies, their light has passed through billions of years of intervening gas on its way here, and neutral hydrogen absorbs at a very specific wavelength. Look at quasars from after reionization, and the absorption is patchy and thin. Look at ones from before it finished, and the absorption becomes a wall, blacking out that part of the spectrum entirely. You can see the fog closing back in as you look further away, which is to say, further back. And now, the galaxies begin. And this is where the story has been rewritten in the last few years. In public. In real time. Until recently, the accepted picture was that early galaxies should be small, faint, ragged, and blue, assembled from mergers of smaller pieces, growing gradually, taking their time to build up mass and structure. That is what the models predicted, and it seemed reasonable. Then the James Webb Space Telescope opened its eye in 2022 and started looking at the earliest epochs anyone had ever resolved. and the early universe turned out to be brighter and busier than expected, and galaxies appeared that were more luminous than the models allowed at that age. Some looked to have assembled surprising amounts of stellar mass in a few 100 million years. Some had structure already, orderly rotating disks, when they should still have been chaotic. The current record holder was confirmed in a peer-reviewed paper at the start of 2026, and its light left when the universe was about 280 million years old. That is 2% of the current age, and it is not a faint smudge at the limit of detection. It is bright. Now, is this a crisis for the Big Bang, as it has been reported in some places? No, it is not that. The framework is not in trouble. What is in trouble is the detailed modeling of how quickly gas turns into stars in the very first galaxies, which is a real and interesting problem, but a much smaller one. And the likely answers are mundane. Perhaps early star formation was unusually efficient because the gas was dense and unenriched. Perhaps the earliest stars really were far more massive on average, making each galaxy brighter without needing more mass. Perhaps there was less dust in the way. Several of those together would be enough. Researchers on the Discovery team wrote that redshifts previously considered unimaginable no longer seem far away, and that they expect to push the frontier closer to the era of the very first stars. Which means this section of the story will probably be different in 5 years. That is not a weakness. It is what a young science looks like from the inside. There is another puzzle from this era, and it is a bigger one. The black holes. At the centers of galaxies sit supermassive black holes, millions to billions of times the mass of the Sun. The Milky Way has one, about 4 million solar masses, and it is quiet and well-behaved. Fine. But quasars have been found from when the universe was less than 700 million years old, powered by black holes already weighing 1 billion suns. So how did they get so large so fast? Nobody can quite explain it. A black hole formed from a collapsing star starts at a few tens of solar masses, and there is a speed limit on how fast it can grow by swallowing gas, because infalling material heats up, and the radiation pressure blows the rest of the supply away. Run the numbers with a stellar seed and normal growth, and you cannot reach 1 billion solar masses in 700 million years. It is not close. So either the seeds were much larger to begin with, perhaps enormous gas clouds collapsing directly into black holes of tens of thousands of solar masses without ever being stars, or the growth limit can be broken in the messy conditions of the early universe, or something else is happening that we have not thought of. Webb has been finding surprisingly heavy black holes in surprisingly small early galaxies, which has made the problem sharper rather than softer. I like that this one is still open. Something very large was happening in the first few 100 million years, and we do not know what it was. By around 1 billion years, the universe looks recognizable in outline. Galaxies exist in enormous numbers, small and irregular and full of young blue stars. The gas between them is transparent. Black holes are feeding at the centers of the biggest ones, blazing as quasars, some of them outshining every star in their host galaxy combined. The great cosmic web is taking shape, with galaxies strung along filaments and clustered where filaments meet, and vast empty voids between, all following the pattern of those quantum ripples from the first instant. And it is worth pausing here, before we go further forward, because I have been mentioning dark matter as though it were a settled background detail, and it is neither settled nor a detail. It is most of the mass in the universe, and every structure in this story was built on top of it. The evidence starts in the 1930s with an astronomer named Fritz Zwicky studying a cluster of galaxies in the constellation Coma. He measured how fast the galaxies were moving relative to each other, and the speeds were far too high. There was not nearly enough visible material in the cluster to hold it together gravitationally. At those velocities, the galaxies should have scattered long ago. He concluded that most of the mass must be something unseen, and used a term for it that translates as missing matter, and was almost entirely ignored for the next 40 years. The idea came back in the 1970s, mainly through the work of Vera Rubin and Kent Ford, who measured how fast stars orbit inside individual spiral galaxies. The expectation was straightforward. In the solar system, planets further from the sun orbit more slowly, because nearly all the mass is in the middle. Galaxies should behave the same way, with outer stars lagging behind inner ones. They do not. The outer stars in spiral galaxies orbit at roughly the same speed as the inner ones, all the way out, further out than the visible starlight extends, which only works if there is a great deal of mass out there that is not shining. Rubin measured galaxy after galaxy and found the same result every time, and the consistency of it is what finally made the field pay attention. Since then, the evidence has piled up from directions that have nothing to do with each other. The way distant galaxies are distorted by the gravity of foreground clusters, which maps the mass directly and finds several times more than the light accounts for. The temperature of the hot gas in clusters, which requires more gravity than the visible matter provides. The fine pattern in the oldest light, which depends sensitively on how much matter was present and how it behaved, and which pins the amount at about 5 times the ordinary matter. And the very existence of galaxies, which could not have assembled in the available time without extra gravity doing the early work. So the case is strong. But what is it? That remains completely unknown. Could it simply be ordinary matter that happens to be dark? Cold gas, rogue planets, burnt-out stars? No. Ordinary matter in that quantity would have altered the nucleosynthesis in the first minutes and the pattern in the oldest light, and it did not. It appears to be something that interacts through gravity, and almost nothing else. It passes through itself. It passes through you. It does not clump into stars or planets, because it has no way to shed energy, which is why it forms diffuse halos rather than compact objects. For decades, the leading candidates were heavy, sluggish, weakly interacting particles, and enormous detectors were built to catch one. Tanks of liquid xenon, shielded and buried under mountains, watched patiently for a single nudge. They have found nothing. The most natural mass ranges have been searched and excluded, which has pushed attention toward much lighter candidates, or much heavier ones, or ideas that abandon the particle picture altogether and modify gravity instead. Those modified gravity proposals have their own serious difficulties, particularly with clusters and with the oldest light. So a quarter of the universe is a question mark, and the question mark has been there for 90 years, and the searches continue. But whatever it is, it did the essential work. Because the shape of the universe now, the arrangement of everything, was drawn by dark matter first. Picture the process. Those quantum ripples from the first instant left some regions marginally denser than others. Dark matter, feeling only gravity, immediately began falling toward the dense spots. It could not be held up by light pressure because it does not interact with light, so it had a head start of hundreds of thousands of years on everything else. By the time the fog lifted and ordinary gas was free to move, dark matter had already built a network of wells and ridges and filaments across the entire universe. Then the gas fell in and lit up. What emerged is the largest structure that exists, and it is called the cosmic web. Galaxies are not scattered evenly through space. They sit along enormous filaments, threads of galaxies and gas, hundreds of millions of light years long, arranged like the strands of something spun. Where filaments cross, you get clusters, thousands of galaxies bound together. And between the filaments are the voids, immense, nearly empty regions, tens or hundreds of millions of light years across, containing almost nothing at all. Surveys have now mapped this out to great distances, and the maps look startlingly like a biological cross-section or a network of roots or foam. It was not designed to look that way. It is what gravity does to a field of tiny random fluctuations given billions of years and no interference. And the correspondence between the predicted Webb and the observed one is one of the most convincing results in cosmology. You can run the whole thing in a computer. Start with the fluctuation pattern read off the oldest light, add the measured amounts of dark matter and ordinary matter and dark energy, apply gravity, and let it run for 13.8 billion years of simulated time. The result is a web with the same statistical structure as the real one. Same filament lengths, same void sizes, same clustering. It works. And the Milky Way sits on the edge of a filament in a modest group, on the outskirts of a larger structure, not in a cluster, not in a void. A fairly unremarkable address, which is exactly what you would expect, since most galaxies live in fairly unremarkable addresses. And all of it grew from irregularities that were smaller than an atomic nucleus in the first fraction of the first second. And then comes the busiest period in the history of the universe. Between roughly 2 and 4 billion years after the beginning, star formation across the cosmos hit its peak. Astronomers call it cosmic noon. Galaxies were forming stars at something like 10 to 20 times the rate they do today, and the reason is straightforward. There was still an enormous amount of cold gas available, and galaxies were close together, so mergers were frequent and violent, and mergers compress gas and trigger bursts of star formation. So what would the sky have looked like from a planet at cosmic noon? There would have been very few planets suitable for looking from, but the view would have been far more dramatic than ours. Galaxies large in the sky rather than faint smudges, bright blue star-forming regions, supernovae going off constantly. It was a spectacular and thoroughly inhospitable time. Radiation levels were high, heavy elements were still scarce, and everything was being disrupted by something else. And most of the stars that have ever existed formed in this window. The universe has been quietly winding down ever since. Star formation today runs at a few percent of the peak rate because the gas has been used up or heated or blown out, and the galaxies have drifted apart. We are living in the long, slow evening of star formation, which is a slightly melancholy fact and also a comfortable one. Things are calmer now, and somewhere in that busy period, our own galaxy started to come together. The Milky Way did not form as a spiral. It formed as a mess. The oldest components are the halo stars and the globular clusters, dense spherical knots of ancient stars that orbit at strange angles to the disk, some of them close to 13 billion years old. Those are the survivors of the first assembly. The oldest individual stars in the halo have almost no heavy elements at all, which is how we identify them. They formed from gas that had only been enriched by 1 or 2 generations of supernovae. One of them, a star catalogued as HD 140283 and nicknamed Methuselah, was measured at one point to be around 16 billion years old, which is a problem, because it would have made the star older than the universe. This was genuinely embarrassing for a while. Better parallax data and improved stellar models have since brought the figure down to something in the range of 12 to 14.5 billion years, with uncertainty large enough that it now sits comfortably inside the age of the universe. It is a good example of a number that got revised, and of why single measurements should be held loosely. And the Milky Way grew mostly by eating. Around 10 billion years ago, a fairly large galaxy fell in and was torn apart, and its stars are still identifiable by their peculiar orbits, all moving together in a way that ordinary disk stars do not. That event is now called Gaia Enceladus, named for the space telescope that found the evidence and for a giant in Greek myth. It puffed up the early disk and delivered a substantial amount of material. And there were others. Dozens of smaller galaxies have been absorbed, and their remains are threaded through the halo as long streams of stars, still tracing the orbits they fell in on. The Sagittarius dwarf galaxy is being pulled apart right now, with a stream of its stars wrapped more than once around the Milky Way. And the large and small Magellanic clouds, visible from the southern hemisphere as faint patches, are on their way in. So the galaxy you live in is a composite, built out of the shredded remains of dozens of others, still digesting, with a quiet supermassive black hole in the middle and a thin flat disk of gas and young stars that only settled into its current smooth spiral shape in the last several billion years. And in that disk, about 8 or 9 billion years into the story, in a perfectly ordinary spiral arm, a cloud of gas was starting to lean toward collapse. So let's slow down here, because we have arrived at the part of the story that produced you, and it happens surprisingly late. The universe was about 9.2 billion years old when the sun formed, which means that for 2/3 of all of cosmic history, there was no sun and no Earth and no solar system. Everything we have covered so far, the whole first 2/3, happened before there was any of this. And that surprises people. We tend to imagine the Earth as an early feature of the universe. It is a late one. 4.6 billion years ago, in a molecular cloud somewhere in the disk of the Milky Way, a region of cold gas and dust became unstable. Something probably nudged it. Perhaps a nearby supernova shockwave, which is a popular candidate because certain isotopes found in the oldest meteorites decay quickly and must have been created very shortly before the solar system formed. Something violent happened next door at more or less the right moment, and the cloud began to fall inward. Most of the material went to the center and became the sun. The rest flattened into a spinning disk, because a collapsing cloud with any rotation at all must spin faster as it shrinks, and a spinning cloud cannot fall inward along its equator as easily as along its poles. So it pancakes. Every planetary system forms this way, which is why the planets of the solar system all orbit in roughly the same plane and the same direction, and why we can see other systems doing the same thing right now in nearby star-forming regions. Within that disk, dust grains began to stick, ice and silicate and metal, colliding gently, clumping into pebbles, then boulders, then bodies large enough for their own gravity to matter. The oldest solid material anyone has ever held, tiny inclusions inside certain meteorites, dates to about 4.568 billion years ago. Those grains are older than the Earth. Some of them are sitting in museum collections, and they condensed from the disk before there were planets to condense onto, and planet building was fast and rough. Perhaps a few tens of millions of years to go from dust to worlds. Bodies collided constantly, sometimes merging, sometimes shattering. The gas giants formed further out where it was cold enough for ice to survive, and their gravity reshaped the whole system, flinging some material inward and much of it out entirely. The Earth was essentially finished by 4.54 billion years ago, and it was not remotely a planet you would recognize. Molten in large parts, no oxygen in the air whatsoever. And then, roughly 30 million years after it formed, something about the size of Mars hit it. So where did the moon come from? From that. The impactor has a name, Theia, and the collision is the leading explanation. The collision was catastrophic and probably not perfectly head-on. A large quantity of material from the outer layers of both bodies was thrown into orbit as a hot ring of vapor and debris. And that ring cooled and gathered and became the moon, close in at first and much larger in the sky than it is now. It has been drifting outward slowly ever since, and it is currently about 3.8 centimeters further away each year, which we know precisely because Apollo astronauts left mirrors on the surface and we bounce lasers off them. That is the origin of the object in your window. A fragment of a collision 4.5 billion years ago, still receding at the speed a fingernail grows. And the early Earth cooled faster than anyone used to think. Zircon crystals from Western Australia, which are exceptionally durable and can be dated with great precision, go back about 4.4 billion years, and their chemistry suggests liquid water was present at the surface. So there were oceans remarkably early, within about 150 million years of the planet forming. There is an old story that the early solar system suffered a delayed storm of impacts around 3.9 billion years ago, called the Late Heavy Bombardment. And you will still see it in a great many documentaries. The evidence for it has weakened considerably. It was based largely on the ages of lunar rocks gathered by Apollo, and it now looks likely that those samples were biased toward a single very large impact event rather than recording a system-wide spike. The current view leans toward a bombardment that simply declined steadily from a violent beginning, which is less dramatic and probably closer to true. And then, at some point in that first billion years, on a hot, wet, chemically active young planet, something began to copy itself. How? Nobody knows. This is the largest unsolved problem in biology, and it is genuinely open, in the same way the first instant of the universe is open. There are good candidate environments. Alkaline hydrothermal vents on the seafloor, where mineral chimneys create natural chemical gradients and tiny compartments. Tidal pools going through wet and dry cycles, which can drive molecules to link into chains. Both have laboratory support, and neither has produced life in a beaker. What we have instead is timing. The oldest widely accepted microbial fossils are around 3.5 billion years old, from the Dresser Formation in Western Australia. There are older claims, structures in Greenland rocks dated to about 3.7 billion years, and carbon inclusions suggesting biological processing at close to 4 billion. Those older claims are contested, and the arguments are technical and unresolved, because rocks that old have been cooked and squeezed until distinguishing a fossil from a mineral formation becomes genuinely hard. But the direction of the evidence is clear enough. Life appeared quickly, within a few 100 million years of the oceans existing, and possibly within a much shorter window than that. Whatever the process was, on this planet, it did not require a long wait, and once it started, it was patient, extraordinarily patient. For the next roughly 2 billion years, life on Earth was single-celled and microscopic, and that was all. There were no plants and no animals, and nothing at all you could see without a microscope. Just bacteria and archaea, in mats and films and colonies, quietly running chemistry. That is a span of time longer than the entire history of the Earth since. If you wanted to find the boring part of the story, this is a much better candidate than the Dark Ages. But one of those microbes invented something that would remake the planet. Photosynthesis, of the kind that splits water and releases oxygen as waste. Cyanobacteria worked this out somewhere over 3 billion years ago, and it was an enormously effective trick because sunlight and water and carbon dioxide are all abundant, and the waste product was a poison. Oxygen is highly reactive, and to the anaerobic life of the time it was lethal. For a long while the Earth absorbed it. Oxygen reacted with dissolved iron in the oceans, and with rock, and with methane in the atmosphere, and it was consumed as fast as it was produced. The iron settled out in immense banded layers that are still mined today. And if you have ever seen a photograph of banded iron formation, those beautiful red and black stripes, you are looking at the residue of the first oxygen crisis. So why did it take so long to change the air? Because the sinks had to fill up first. And eventually they did. Around 2.4 billion years ago, free oxygen began accumulating in the atmosphere, and the composition of the air changed permanently. This is called the Great Oxidation Event, and it was very likely the largest mass extinction in the history of life, killing off an unknown fraction of everything then living. It also stripped methane from the atmosphere, weakening the greenhouse effect, and may have helped trigger a glaciation so severe that ice may have reached the tropics. Life poisoned its own world, nearly froze it, and then built everything else out of the wreckage. Every animal that has ever existed depends on the waste product of that catastrophe. You are breathing it right now. Somewhere around 1.8 to 2 billion years ago, one cell swallowed another and did not digest it. The swallowed cell was a bacterium capable of using oxygen efficiently, and instead of being broken down, it stayed and reproduced. And its descendants are the mitochondria in every cell of your body. They still have their own separate DNA, inherited only from your mother, a small looped remnant of a free living organism absorbed 2 billion years ago. That merger is the origin of complex cells. Everything with a nucleus, every plant, every fungus, every animal, descends from that single event. Then another long wait. Complex single cells for another billion years. Some multicellular experiments. A severe series of global glaciations between 720 and 635 million years ago, when the planet may have been almost entirely ice-covered. And then, 538.8 million years ago, by the current international definition, the Cambrian. Animal body plans appeared in the fossil record in what looks like a sudden burst. Eyes, shells, legs, guts, hard parts that fossilize well, which is part of why it looks so sudden, since soft animals leave much less behind. Almost every major group of animals alive today traces to that interval. Predation became a serious business, and once something is hunting you, there is enormous pressure to move faster and see better and grow armor. After that, the pace of the story picks up in a way that is almost disorienting compared to what came before. Plants moved onto land around 470 million years ago. Forests followed, and with them the first substantial land animals. Around 252 million years ago, the worst extinction in the record nearly ended complex life altogether, with something like 90% of marine species lost, most likely driven by immense volcanic eruptions in what is now Siberia. Life recovered, as it always has. Dinosaurs dominated for well over 100 million years, which is a far longer run than mammals have had. 66 million years ago, an asteroid about 10 kilometers across struck what is now the Yucatan Peninsula and left a crater 180 kilometers wide and ended them. Mammals, which had been small and nocturnal and unremarkable for 150 million years, inherited the vacancy. Primates appeared. The line leading to us split from the line leading to chimpanzees around 6 or 7 million years ago. Anatomically modern humans show up roughly 300,000 years ago in Africa. And then everything you would call history happens in a sliver so thin it barely registers. Agriculture, about 12,000 years ago. Writing, about 5,000. The realization that the Earth orbits the Sun, 500 years. The discovery that other galaxies exist, 100 years. The discovery of the oldest light, 60 years. 60 years. That is how long anyone has known that the universe had a beginning that left a trace. Everything in this script that goes further back than a few thousand years is knowledge that arrived within a single human lifetime. And it is worth asking how any of that ordering is known, because I have been handing you dates all night as though they were simply available, and they are not. Every number in this story had to be extracted from something. There are essentially 4 independent methods, and they were developed by people who were not working together and who often did not much like each other's fields. The first is radiometric dating, and it is the one that fixes the Earth and the solar system. Certain elements are unstable and decay into others at a rate that does not vary with temperature or pressure or chemistry. Uranium becomes lead, potassium becomes argon, rubidium becomes strontium. If you can measure how much of the parent and how much of the daughter a rock contains, and you know the decay rate, you know how long the clock has been running. The technique was worked out in the early 20th century, and it immediately caused trouble because it gave ages for rocks far older than most geologists and physicists were willing to accept. Lord Kelvin had calculated from cooling rates that the Earth could be no more than 100 million years old, and he was extremely confident about it. And he was wrong, because he did not know about radioactivity, keeping the interior warm. The definitive figure came in 1956, when Claire Patterson measured lead isotopes in a meteorite and got 4.55 billion years for the age of the solar system. That number has barely moved since. He then spent much of the rest of his career fighting industrial lead contamination, having become intimately familiar with how much of it there was. The second method is stellar ages. A star's brightness and color and composition together constrain how long it has been burning. Because the physics of stellar interiors is well understood, and the rate at which a star of a given mass consumes fuel is calculable. Apply that to the oldest stars in the halo and to globular clusters, and you get ages in the range of 12 to 13.5 billion years, which is a completely independent line of evidence based on nuclear physics rather than on cosmology, and it agrees with the cosmological age. Any theory that made the universe younger than its oldest stars would be dead on arrival. And for a period in the 1990s that looked like a real possibility, which was uncomfortable for everyone. The third method is the distance ladder, and it is the one that gives the expansion rate and therefore the timescale of the whole thing. It works in rungs, each calibrating the next. Nearby stars can be measured by parallax, which is simple geometry, watching a star appear to shift slightly as the Earth moves from one side of its orbit to the other. Parallax then calibrates certain pulsating stars whose brightness is tied to the period of their pulsation, a relationship discovered by Henrietta Leavitt at Harvard in 1912 while cataloging photographic plates for a modest wage. Those stars then calibrate a particular kind of exploding star that always reaches nearly the same peak brightness, which is bright enough to see across billions of light years. Each rung inherits the uncertainties of the one below it, which is precisely why the disagreement over the expansion rate has been so hard to settle. And the fourth is the oldest light itself, which is the most precise of all. The fine pattern of hot and cold spots contains a great deal of information, because the sizes of the spots depend on the composition and geometry of the universe at that moment, and the way those sizes are distributed can be fitted to a model with a handful of parameters. Fit it well enough, and the age falls out, along with the amounts of ordinary matter and dark energy. That is where the figure of 13.787 billion years comes from, with an uncertainty of about 20 million years, which is a precision of roughly 1 part in 700. 4 methods: radioactive decay in rocks, nuclear physics in stars, geometry across space, and the statistics of a pattern in the sky. They rely on entirely separate physics and separate instruments and separate assumptions, and they agree. And that agreement is the actual reason to believe any of this. Not because one measurement was clever, but because measurements that had no obligation to match each other did anyway. If the age of the universe were wrong, you would expect at least one of those 4 to disagree loudly, and none of them does. There is a similar convergence for the ordering of life on Earth. The rock layers give a sequence because younger sits on older, which was worked out before anyone could date anything. Radiometric dating then attaches actual numbers to particular layers. Fossils in those layers give a biological sequence, and molecular clocks, comparing the genetic differences between living species, give an independent estimate of when lineages diverged. Those methods also broadly agree, and where they disagree, which happens, the disagreements are the interesting parts and get argued about in the literature for decades. So the order in this script is not a story someone assembled for narrative convenience. It is a sequence that 4 or 5 unrelated lines of evidence keep independently reproducing, which is about as good as knowledge gets. Which brings us to now. 13.8 billion years in, give or take, on a Wednesday, in a dark room. I want to spend a little time on the present before we go forward, because the present is a genuinely peculiar moment to be alive in, and not for the reasons people usually give. The universe is currently expanding, and the expansion is accelerating. That acceleration was discovered in 1998 by 2 competing teams measuring distant exploding stars, and both were expecting the opposite result. They thought gravity would be slowing the expansion down, and the question was only by how much. Instead, the distant supernovae were fainter than they should have been, meaning further away than expected, meaning the expansion has been speeding up for the last several billion years. Whatever is doing that is called dark energy, and the name is a placeholder for our ignorance. It accounts for roughly 68% of the energy content of the universe. Dark matter is another 27. Ordinary matter, everything made of atoms, every star and planet and person and cloud of gas, is about 5% of the total, and the 5% is the only part we understand. So the honest summary of 13.8 billion years of cosmic history is that we have a detailed and well-tested account of the small minority component, and 2 large placeholders where the majority should be. And there are 2 arguments happening right now, this year, that could reshape parts of this story. The first is about the expansion rate itself. There are 2 good ways to measure how fast the universe is expanding today. One works from the early universe, reading the pattern in the oldest light and calculating forward, and it gives a value of about 67 kilometers per second for every megaparsec of distance. The other works locally, climbing a ladder of distance measurements out from nearby stars, and it gives about 73. Both methods have been refined for years. The error bars have shrunk, and the 2 numbers have not converged. This is called the Hubble tension, and it has been sitting there for over a decade now, stubbornly. Some teams, using red giant stars rather than the traditional pulsating variable stars as calibrators, get an intermediate value around 70 with wider uncertainty, which would mean there was never a real conflict, only imperfect measurements. Other teams have taken that argument apart and reaffirmed the higher local value with increasing confidence. A high-precision result published in the spring of 2026, using a network of several independent distance methods cross-checked against each other, landed firmly on the higher side and deepened the disagreement rather than easing it. As of tonight, it is not resolved, and thousands of papers have been written about it. So, which is right? The 67 or the 73? Nobody can say yet. And if the gap is real, it means something is missing from the model. Perhaps something in the early universe that we have not accounted for. Perhaps something about the nature of dark energy. Perhaps something about gravity itself on the largest scales. The second argument is about dark energy, and it is newer and stranger. The simplest version of dark energy is a cosmological constant, a fixed property of space, the same density everywhere and at every time, never changing. Einstein wrote such a term into his equations in 1917 for entirely the wrong reasons, and then abandoned it when the expansion was discovered. It came back in 1998 and has been the standard assumption ever since. But the dark energy spectroscopic instrument on a telescope at Kitt Peak in Arizona has been building the largest three-dimensional map of the universe ever made. In April of 2026, it completed its planned 5-year survey, having measured the positions and distances of more than 47 million galaxies and quasars. And when its results are combined with the oldest light, and with supernova surveys, and with gravitational lensing, they show a persistent hint that dark energy may not be constant at all, that its effect may have been stronger in the past and may be weakening now. If that holds up, it would mean the fate of the universe is not what has been assumed for a quarter century. It would mean dark energy is a field that evolves with its own history and its own future, rather than a fixed feature of space. And it might not hold up. This needs saying clearly. The signal has not reached the standard of confidence that physicists require before treating something as established. And there is a long and honorable history in astronomy of intriguing hints that dissolved when better data arrived. Some analyses published this year argue the effect is an artifact of comparing two datasets that do not quite agree with each other for unrelated reasons. Results from the full 5-year sample are expected next year, and the survey has been extended to keep observing into 2028, precisely because the hint is interesting enough to chase. So we are in the middle of it, not looking back at a settled science, but sitting inside an open question tonight, with the answer arriving in a few years. And there is one more thing about the present that I find the most affecting fact in all of cosmology, and it has nothing to do with instruments. We happen to live at a moment when the universe is legible. The oldest light is still detectable, but it is fading and stretching, and in the far future, it will be undetectable. Other galaxies are still visible, but the accelerating expansion is carrying them away, and in the far future, they will be beyond any possible horizon. Astronomers on a world a few 100 billion years from now, if there are any, would look out at a sky containing only the merged remains of their own local group of galaxies, surrounded by apparently infinite blackness. No other galaxies, no cosmic microwave background, no way to detect the expansion at all, because nothing observable would be receding. They would conclude entirely reasonably and from careful evidence, that they lived in a single island of stars in a static, eternal void. They would be wrong, and there would be no way for them to find out. We are early enough that the evidence is still on the table. That is not a small piece of luck. So let's go forward, from here, into the part of the story that has not happened yet. And the physics for the near part of this is quite solid, not speculation. Orbital mechanics and stellar evolution, which are among the best understood subjects in all of science. In about 4 to 5 billion years, the Andromeda galaxy arrives. Andromeda is the nearest large spiral galaxy, about 2.5 million light-years away, and it is one of the few galaxies moving toward us rather than away, because within a gravitationally bound group, the local pull beats the cosmic expansion. So will they collide? The classic prediction, which you will find in most descriptions, is a direct collision and merger in roughly 4.5 billion years, producing a single large elliptical galaxy, sometimes called Milky Way. That prediction has recently softened, and it is worth being accurate about it. The head-on approach speed is well measured. The sideways motion is not, because measuring the sideways drift of an object 2.5 million light-years away is extraordinarily difficult. Newer analyses, including work published in 2025 that accounts more carefully for the gravitational influence of other nearby galaxies, find that a merger within the next 10 billion years is only around a coin flip. The galaxies may pass close by, disturb each other, and take a very long time to settle, or they may simply miss. Either way, it will not be violent in the way the word collision suggests. Galaxies are almost entirely empty space. Stars do not hit each other. The distances between stars are so vast compared to the sizes of stars that the chance of any two colliding during a galaxy merger is essentially zero. What actually happens is that gravity rearranges everything. Orbits are stirred. Spiral arms are pulled into long streams. Gas clouds do collide, and where they do, there are bursts of star formation. The sky from a surviving planet would change over hundreds of millions of years into something extraordinary. 2 galactic disks tangled across the whole night, and no individual star would notice. Long before that is settled, the sun becomes a problem. The sun has been slowly brightening for its whole life. It is about 30% more luminous now than when it formed, and it will keep going. Because as hydrogen fuses into helium in the core contracts and heats, and the reaction rate climbs. In roughly 1 billion years, the increase will likely be enough to push the Earth past the point where oceans can persist. Water vapor is itself a greenhouse gas, so the warming feeds on itself. And the oceans go to the atmosphere, and then the hydrogen escapes to space and does not come back. So the habitable phase of this planet ends about 1 billion years from now, which is sobering only until you notice that it is a very long time, roughly 1/4 of the age of the Earth, and considerably longer than complex animals have existed so far. Then, in about 5 billion years, the core runs out of hydrogen. The sun swells enormously into a red giant, hundreds of times its present diameter, engulfing Mercury and Venus certainly. Will it reach the Earth? That is genuinely uncertain, because the sun will also be shedding mass, which loosens the Earth's orbit and lets it drift outward. So the Earth may be swallowed, or it may survive as a scorched airless rock orbiting through the outer layers of a bloated star. Either way, it will not be a place. And after the red giant phase, the sun sheds its outer layers entirely. They drift away as a glowing shell, a planetary nebula, which is a beautiful object and a badly named one, since it has nothing to do with planets. William Herschel coined the term because through his telescope, these shells looked like small round disks. It stuck, wrongly, the way these things do. What remains at the center is the exposed core, an object about the size of the Earth containing most of the mass of a star, made of carbon and oxygen packed to a density where a teaspoon weighs several tons, a white dwarf, no longer fusing anything, just cooling, slowly, radiating away the last of its heat over an extraordinarily long time. That is the fate of the Sun and of the great majority of stars. Not an explosion, a slow fade. So let's keep going, because the story is barely started. Everything covered so far, from the first instant to the death of the Sun, fits inside the first 20 billion years or so. And the universe has essentially unlimited time ahead of it. The next thing that happens is a slow closing of the sky. If the accelerating expansion continues at roughly its current rate, then galaxies not gravitationally bound to us will keep receding, and the recession will keep speeding up. Eventually, each of them crosses a horizon beyond which its light can no longer reach us, no matter how long we wait, because the space in between is stretching faster than the light can cross it. They do not vanish suddenly. They redshift and dim and slow and fade toward invisibility, hovering at the boundary. Within perhaps 100 billion years, the observable universe will contain nothing but the local group. Our galaxy, Andromeda, the Magellanic Clouds, the Triangulum Galaxy, and a few dozen dwarf companions, all merged or merging into one large elliptical mass. Beyond that, dark. Not empty in reality, but unreachable in principle, which for any observer amounts to the same thing. The cosmic microwave background will still be there, technically, but stretched to wavelengths so long that detecting it would require an antenna larger than the galaxy. All the evidence that we spent the 20th century gathering will be gone. Not destroyed, just out of reach. Meanwhile, the stars are running down. Star formation requires cold gas, and every generation of stars locks some of it up permanently in white dwarfs and neutron stars and black holes, or blows it out of the galaxy entirely in supernovae and stellar winds. The supply is finite, and it is not being replenished. So the rate of star formation, which peaked around 11 billion years ago, continues its long decline. In something like 1 to 2 trillion years, the last new star will form somewhere from the last usable pocket of gas. After that, no more. What remains is the population already burning, and stars burn for wildly different lengths of time depending on their mass. This is the crucial asymmetry of stellar life, and it works in the opposite direction from intuition. The most massive stars are the most extravagant. They have far more fuel, and they consume it so recklessly that they last only a few million years. The smallest stars, the red dwarfs, are miserly. They are dim and cool, and they mix their fuel thoroughly, so they can keep fusing hydrogen for trillions of years. Something like 10 trillion years for the smallest of them. And red dwarfs are the most common kind of star by a wide margin, perhaps 3/4 of all the stars in the galaxy. They are all too faint to see with the naked eye, every single one, including the nearest star to the sun. So the sky, as you know it, full of bright, hot, short-lived stars, is unrepresentative. Most of the universe's stars are small and red and patient, and they will still be burning long after the last bright star has gone. Picture the galaxy in 1 trillion years. No blue stars, no spiral arms, because the arms are patterns in star formation, and there is no star formation. a dim red glow of dwarf stars spread through an elliptical smear with white dwarfs cooling among them. It would be a quiet and rather beautiful place, very dark, almost nothing happening. And then, roughly 100 trillion years in, the last red dwarf exhausts its hydrogen, and the era of starlight ends. Astronomers call what comes next the degenerate era, after the strange state of matter that dominates it. It begins around 100 trillion years from now and lasts an unimaginably longer time. What is left is remnants, white dwarfs, in enormous numbers, the cooling cores of every star that ever lived. Neutron stars, which are the collapsed cores of the most massive stars, city-sized objects with more mass than the sun and a density approaching that of an atomic nucleus, black holes of every size, brown dwarfs, objects that never quite manage to become stars, planets, moons, asteroids, dust, all of it cooling and orbiting in the dark. And the white dwarfs will fade. A white dwarf has no energy source. It simply radiates its stored heat away, and because it is small, it has little surface to radiate from, so it takes an extraordinarily long time. Current estimates suggest something like a quadrillion years or more to cool to the temperature of the surrounding space, at which point the object is called a black dwarf. No black dwarfs exist yet anywhere in the universe. There has not been remotely enough time. Every white dwarf that has ever formed is still warm. Occasional things will still happen in the degenerate era, and they are worth mentioning because otherwise it sounds too quiet. Stellar remnants will collide, rarely, and when two white dwarfs collide, the result can be a brief flare of fusion, a last supernova long after the last star. Objects will be flung out of galaxies by gravitational encounters, one at a time, over trillions of years, until galaxies gradually evaporate. The remaining bound objects will spiral inward. And there is one process that might quietly dismantle everything, and nobody knows whether it happens. Proton decay. The proton appears to be stable. Every proton in your body has been sitting there for 13.8 billion years without incident. But some theories that unify the fundamental forces predict that protons are not quite permanent, only extremely long-lived, decaying eventually into lighter particles. Enormous detectors have been built to look for this. Tanks of ultra-pure water buried deep underground, watched for years. Nothing has ever been seen. The experiments have established that the proton lifetime, if it is finite at all, must exceed something like 10,000 trillion years. So do they decay or not? Nobody knows, and it may be a very long time before anyone does. If protons do decay, then eventually all ordinary matter comes apart. Planets dissolve. Black dwarfs evaporate into radiation. Every atom that has ever existed unmakes itself, and by something like 10 to the power of 40 years, there is essentially no ordinary matter left in the universe. If protons do not decay, the remnants persist far longer, and matter simply sits there, cold and inert, effectively forever, until gravity slowly gathers what it can. Either way, the outcome converges on the same picture, because of what happens next. The black hole era. Black holes are the last structures standing, and they turn out not to be permanent either. In 1974, Stephen Hawking showed that black holes must slowly radiate because of the interaction between the event horizon and the quantum fields around it. And the radiation is absurdly faint. For a black hole, the mass of the sun, it is far colder than the cosmic microwave background, which means such a black hole is currently absorbing more energy than it emits and is slowly growing rather than shrinking. it will only begin to evaporate once the universe has cooled below its own temperature, which will take a long while. But once evaporation starts, it does not stop. And it accelerates, because as a black hole loses mass, it gets hotter, which makes it radiate faster. And the timescales here stop meaning very much. A black hole with the mass of the Sun would take something in the region of 10 to the power of 67 years to evaporate completely. The supermassive black hole at the center of a galaxy, millions or billions of times heavier, would take something like 10 to the power of 100 years. Written out, that is a 1 followed by 100 zeros. There is no useful way to feel that number. Comparisons fail. If you take the entire age of the universe so far, 13.8 billion years, it is not a measurable fraction of that span. It rounds to nothing. And at the very end of its life, after all that patient leaking, a black hole finishes quickly. The last of its mass goes in a final bright flash of particles and radiation, and then it is gone, and the region of space where it was is simply empty. The last flash in the universe will be a small black hole ending, alone, in the dark, an unthinkable stretch of time from tonight. After that comes what is sometimes called the dark era, and there is not much to describe, which is the point. A universe of vastly diluted radiation, stray electrons and positrons drifting light years apart and expanding space. There would be no structure and no events. Nothing at all to mark the passage of time. And can time be said to pass when there is nothing left to change? That may not even be a well-posed question. That is the standard picture, and it is called heat death. Not a violent end, a settling. Everything that could happen has happened, and the universe continues expanding and thinning forever, at a uniform temperature approaching absolute zero, except that it might not go that way, and this is where the two arguments from earlier come back. Because the far future of the universe depends entirely on what dark energy turns out to be. If dark energy is a true cosmological constant, fixed forever, then you get the picture I have just described. Endless expansion at a steady acceleration, everything drifting apart, cooling, thinning, fading, long and gentle and final. If dark energy strengthens over time, the story ends much sooner and much less gently. Expansion would accelerate without limit, and the horizon within which anything could remain bound would shrink. Galaxy clusters would be pulled apart, then galaxies, then solar systems, then planets, then atoms. This scenario is called the Big Rip, and depending on the parameters, it could happen tens of billions of years from now, rather than in an unimaginable future. It is not the favored model, but it has never been ruled out. And if dark energy weakens, which is what those new survey hints tentatively suggest, then the acceleration eases. The expansion might slow and continue coasting forever. Or it might, in some versions, eventually reverse, and everything would fall back together into a hot, dense collapse, sometimes called the Big Crunch, possibly followed by another expansion. In which case the universe is cyclical, and this whole 13.8 billion year story is one iteration of something that has happened before and will happen again. So which ending is it? Nobody knows yet. Those are extremely different endings, and the difference between them comes down to a number that is currently being measured this year from a telescope in Arizona, and argued about in papers appearing every month. I find something restful in that too. The end of the universe is not settled, and the argument is live. And being alive at the moment when a question that large is genuinely open is a rare position to occupy. There are stranger possibilities that I will mention only lightly, because they are speculative, and I do not want to leave you with anything sharp to think about. One is that the vacuum of space is not in its lowest possible energy state, only a stable enough one, in which case it could in principle transition to a lower state, and the properties of physics would change. There is no evidence that this will happen, and the fact that the universe has lasted 13.8 billion years without it happening is fairly reassuring. Another is that if the universe lasts long enough, extraordinarily unlikely events become inevitable. Random fluctuations in a nearly empty space would very occasionally assemble something ordered. Over the timescales involved, that arguably includes structures far more complex than a black hole. Physicists take this seriously enough to argue about it in journals and generally treat it as a sign that some assumption in the calculation is wrong. It is a puzzle rather than a prophecy. And one more, which is the honest one. All of this assumes that the physics we have measured over a few hundred years, in a very small region, at a particular moment, continues to apply for the next 10 to the power of 100 years. That is a large assumption. It might be right, but the history of this subject is a history of confident extrapolations that turned out to need revision, and the only sensible attitude toward the far future is interest rather than conviction. So let's come back down, all the way back, from the last black hole, through the long dark, past the fading of the last red star, to the here and now, to 13.8 billion years, and a Wednesday, and this room, because I want to finish where we began. With the atoms, you are made of the story we have just walked through, not metaphorically, physically, and in a way that can be traced element by element, and I want to go through it slowly because it is the part worth taking with you. Start with the hydrogen. About 2/3 of the atoms in your body are hydrogen, mostly locked into water. Every one of those nuclei is a single proton that formed in the first millionth of a second, when the universe cooled enough for quarks to bind, and then survived the annihilation that removed almost everything else. They have never been broken since. They are original material, 13.8 billion years old, older than any structure in existence. There are more of them in a single glass of water than there are stars in the observable universe. Then, the oxygen. By mass, you are mostly oxygen, since water is heavy on that side. Not one atom of it existed for the first 100 million years or more. It was made in the cores of massive stars, in the fusion sequence that runs from helium to carbon to oxygen, under pressures and temperatures found nowhere else. And it only got out because those stars died and blew themselves apart. Every oxygen atom in every breath you take tonight was released by a dying star. The carbon, which is the backbone of every molecule that makes you a living thing rather than a mineral, came from the same process. It requires 3 helium nuclei to combine, which happens only in the dense interiors of aging stars, and it happens through a resonance so finely balanced that Fred Hoyle predicted the resonance must exist purely because carbon does. He was right, and it was found. That is one of the more remarkable pieces of reasoning in the history of physics, and he did it while being wrong about the Big Bang. The nitrogen in your DNA, from stellar fusion, the calcium in your bones, from stellar fusion and from supernovae, the iron in your blood, carrying oxygen to your cells right now, forged in the last stages of massive stars and in the thermonuclear detonation of white dwarfs. Iron is where fusion stops paying, which is why massive stars collapse once they build an iron core, and why iron is so abundant, and why your blood is the color it is, the phosphorus in your cell membranes, the potassium and sodium moving across your nerve cells, which is how you are hearing this, the zinc, the copper, the iodine. All of it manufactured in stars and scattered by their deaths and mixed into a cloud of gas and dust in the disk of the Milky Way and gathered up 4.5 billion years ago into a disk around a new star and clumped into a planet and cycled through rock and ocean and atmosphere and countless living things for billions of years and assembled into you temporarily according to instructions inherited from a chain of ancestors that has never once been broken since it started, somewhere near a vent or a shoreline, close to 4 billion years ago. Nothing in that sequence was aimed at you. There is no step in it that was for your benefit. And yet every step had to happen in order for you to be lying here. The heaviest elements, the gold and the platinum and the uranium, needed something even more extreme. For a long time, the assumption was that ordinary supernovae made them. It now looks like a substantial fraction, possibly most, comes from collisions between neutron stars, and those are so rare and so violent that they briefly outshine galaxies and warp space enough to be detected as gravitational waves. One such collision was observed in 2017 in both gravitational waves and light, and the spectrum showed freshly minted heavy elements streaming out of it. If you are wearing a gold ring, it was very likely made in the final milliseconds of 2 dead stars falling into each other somewhere in the galaxy before the sun existed. And the light that got the whole thing started is still passing through. Every second, the afterglow of recombination is arriving at your body from every direction. Photons that left when the universe was 380,000 years old and have been traveling ever since, uninterrupted, for 13.8 billion years, ending their journey in a dark bedroom against your skin. Not many of them do much. They are extremely cold. But they are here, constantly. And they have been here the whole time you have been listening. And the neutrinos, from the first second, streaming through the mattress and the floor and the earth without noticing any of it. You are not observing this universe from outside it. You are a temporary arrangement of the oldest material there is, sitting in the middle of a process that started before there were stars, still receiving light from the beginning of it. So before we let all of this go, I want to lay the whole thing out one more time in a form that fits in the hand, because 13.8 billion years is not a quantity anyone can feel. And there is an old trick for making it feelable that Carl Sagan used to use, and it is worth doing slowly. Compress the entire history of the universe into a single calendar year. The beginning falls at midnight on the 1st of January. Tonight is the last instant of the 31st of December. On that scale, 1 month is a little over 1 billion years. 1 day is about 38 million years. 1 second is around 440 years. So, midnight, the 1st of January, everything begins. Inflation, the separation of the forces, the Higgs field switching on, the annihilation that left the residue you are made of, the first protons, the first helium, all of it inside the first tiny fraction of the first second of the first minute of the year. If you blinked at midnight, you missed the entire foundation of physical reality. About 15 minutes past midnight, the fog lifts. The first atoms form, and the oldest light is released and begins its journey to this room. Then darkness for the rest of the night. The first stars ignite around the 6th of January. The most distant galaxy anyone has yet confirmed is shining by the 8th. Reionization finishes near the end of the month, the last global change of state the universe will undergo, done and dusted in January, February, and March. Galaxies assembling and colliding, quasars burning at their centers, star formation climbing toward its peak around the end of March. Most of the stars that will ever exist are being made in these weeks. April. The Milky Way is eating its neighbors. The galaxy that became the halo falls in and is torn apart around the middle of the month. May, June, July, August. 4 months of galaxies quietly turning, stars forming and dying, enriching the gas with carbon and oxygen and iron, generation after generation, building up the material that everything later will be made from. Nothing you would call an event, just patient stellar recycling for 4 billion years. And then the 1st of September, the sun forms. 2/3 of the year has already gone by and the solar system is only starting now. A few days later, the Earth is finished and the moon has been knocked out of it. By the middle of September, something on the surface is copying itself, and after that the entire rest of the calendar is life on one planet, and almost all of it is invisible. The whole of late September, October, and the first week of November is microbes. That is 6 weeks of the year in which the most complicated thing on Earth is a single cell. The atmosphere fills with oxygen in the last days of October, which kills most of what is living and makes everything after it possible. Complex cells with mitochondria arrive around the 8th of November, then another 5 weeks of very little, biologically speaking, punctuated by a near total freezing of the planet in the middle of December. The 17th of December. Animals with eyes and shells and legs appear in the fossil record. Everything you would recognize as an animal belongs to the last 2 weeks of the year. Plants move onto land on the 19th. The largest extinction in the record happens on Christmas Eve. Dinosaurs get the rest of Christmas week, which is a decent run, and the asteroid arrives late on the 29th. And now it is the 31st of December, and mammals have the day to themselves. Our line splits from the chimpanzee line at around 7:30 in the evening. Anatomically modern humans appear about 11 minutes before midnight. Everything before that is pre-human. Agriculture begins 27 seconds before midnight. Writing, about 11 seconds. Every civilization, every empire, every religion, every war, every book, every piece of music ever composed, all of it inside the last 11 seconds of the year. Copernicus works out that the Earth goes around the Sun about 1 second before midnight. Hubble discovers that other galaxies exist 0.2 of a second before midnight. Penzias and Wilson find the oldest light roughly 1/10 of a second before midnight. And everything in this script that reaches back beyond a few thousand years has been learned in that final 1/10 of a second. A human lifetime on this calendar is about 0.2 of 1 second. And it is tempting to hear all that and feel small. But is small the right response? I want to suggest the opposite, or at least something adjacent to it. Because in the last fraction of the last second of that year, a temporary arrangement of hydrogen from the first minutes and carbon from dead stars worked out the whole preceding calendar from inside it, without ever leaving the surface of one planet, using light that happened to be passing through. That is what happened. That is where we actually are. So let's come all the way back down now. Back from the last black hole evaporating into the dark, and the long dark before it, and the fading red dwarfs, and the sun as a cooling white ember, and Andromeda tangled across the sky. Back through the argument happening this year over what dark energy is doing. Back to now. Back to one ordinary spiral galaxy, on one arm of it, 26,000 light-years out, from a quiet supermassive black hole, taking 230 million years to complete a single lap. Back to one yellow star, halfway through its life, 4.5 billion years old, and about 30% brighter than when it started. Back to the third planet out, most of it water, oxygen in the atmosphere, because something poisoned the place 2.5 billion years ago and never cleaned up. Down through the atmosphere, over the dark side of the planet, where it is night, which is only a shadow, and the shadow is moving. Down to one country, one town, one building, one room. This room, and the bed you are lying in, and the weight of the blankets, and the particular temperature of the air tonight, and whatever small sounds are in the room with you. That is where the journey ends. Not out there. Here. Your body is warm. It is holding a temperature within a fraction of a degree, using energy from food, which came from plants, which used sunlight. And that sunlight was made by hydrogen fusing into helium in the core of the sun about 100,000 years ago, then slowly working its way out. The light on your skin during the day is not new. It takes an extraordinarily long time to get out of the sun and 8 minutes to cross the space afterwards, and your blood is moving iron around, forged in stars that died before the sun was born. Your bones are holding calcium made the same way. Your nerves are firing using sodium and potassium, moving across membranes built on phosphorus, all of it stellar in origin. The water in you is 2/3 original hydrogen from the first minutes of the universe. You are the oldest material there is, arranged into something that can lie in the dark and think about where it came from, and every second, without any effort on your part, the afterglow of the young universe is passing through you, from every direction, cold and faint and completely harmless. It has been traveling for 13.8 billion years, and it ends here, in this room, tonight, on you. You don't have to do anything with that. You don't have to remember the order of it. There will be no test in the morning on whether recombination came before reionization, or how long a white dwarf takes to cool, or the difference between the degenerate era and the black hole era. The dates can go. The numbers can go. The 13.8 billion years, the 380,000, the 1 part in a billion that survived, the 67 and the 73, that nobody can reconcile. Let all of it drift out of your hands. It was never yours to carry. It was just something to listen to on the way down, because none of it needs anything from you. The expansion was underway for billions of years before there was anyone to notice it, and it will carry on for billions more after everyone has gone. The oldest light will keep raining softly through this room, whether or not you are awake to receive it. The neutrinos from the first second will keep passing through the mattress. The sun will keep fusing hydrogen for another 5 billion years without supervision. Andromeda will keep coming, or not, on its own schedule. The last black hole will evaporate in its own time, an unthinkable distance from tonight, with nobody watching, and that is fine, and that was always going to be fine. So you can rest. You have permission to let the whole vast thing continue on its own tonight. Your only task, the only thing being asked of you right now, is to lie here and be a small, warm, gathered together place in the middle of it. To breathe, to be held by a planet that has been holding things for 4.5 billion years. To be, for a little while, just a quiet body in a quiet room, made of ancient hydrogen and the ash of dead stars, on a small blue world, on one arm of one ordinary galaxy, 13.8 billion years into a story with no known ending. And that is enough. That is more than enough. The room is dark. The bed is holding you. The universe is carrying on, out there, in the deep, where it belongs. And you do not have to go anywhere, or know anything, or be awake for any of it. Let your breathing slow. Let the dates fade. Let the galaxies drift. So just rest now. It will all still be here in the morning, and so will you. Good night.